record. I believe this is working now. Okay. So welcome to my term project presentation. My paper was about the design of biodegradable zinc alloys. This is quite important, and let me give you some backstory, some information. This is quite important because magnesium alloys and biodegradable plastics are already used in biodegradable implants, but they really cannot carry much load. They have an ultimate tensile strength lower than 350 megapascals, and that is at the best. So what they can be used is, at most screws, pins, like small things that should not at least carry much weight. So one smart man decided to try zinc. Okay, can I pass? Okay, there we go. So we're gonna use zinc, but how? So what the researchers did was they selected 8 elements. These elements are already good for bones in general. They created binary alloys with zinc in different concentrations, like 0.1%, 0.4%, 0.8%. They examined these alloys' strength, surface structure, and biocompatibility. And it turns out these zinc and lithium alloys, they are pretty good actually. I'm gonna show you the pictures just in a second. These are the microstructures, not very important. These are their tensile strengths, these alloys tensile strengths. As you can see, this zinc and 0.4 lithium, it has a ultimate tensile strength of above 500 megapascals. That's really, really good. There's also some very cool elongation values, but we'll get to that later. This is their compressive strength. Of course, clearly there are a lot of compressive strength good values too. Again, lithium is pretty rock solid at that too. And this is in general a comparison. Now, I did not want to include this at the beginning, but I believe it gives sort of a good understanding in between the differences of zinc-based and magnesium-based biodegradable metals. Hopefully you can stop the video here and look at the table if you wanted to. Basically, they're both good, but zinc is a bit better in mechanical performance. Okay, what next? Lithium is pretty good. So what the researchers wanted to do was they established lithium was already good, so they decided that they wanted to try a third element with lithium and zinc, but which ones? And they decided to use magnesium for its strength and manganese. I'm so sorry, manganese for their elongation properties. And then the results were amazing, really. So if you look at here, hopefully you can see my mouse. This zinc 0.8 lithium, 0.4 magnesium. It has a ultimate tensile strength of almost 650 megapascals. That's a really good value considering that magnesium alloys can only get to 350. And on the right is the manganese alloys. Now, its ultimate tensile strength is quite impressive again. But what's really impressive about these manganese alloys are their elongation. They elongate almost up to 80% on average. Not an average, but like a good alloy. They elongate up to 80% before failure, and that's like a really, really good number. Okay, so these were the findings, but what does this mean in general life? How are we going to utilize this in society? It means that we can use these zinc, lithium, magnesium alloys where just magnesium doesn't do the job, right? And zinc alloys are strong, they degrade and corrode uniformly, which means they don't fail earlier than expected due to stress concentration. They're also biocompatible. That's very important too. But there's only one minor problem, and that's we need to keep the zinc concentrations low while degrading because high zinc can be toxic. All right, So here's a table. We're gonna go through this table in a bit detail. As you can see, magnesium bits are in here in between 200 and 400 megapascals. They are really only used in bone screws and pins. And then up there is titanium. You know, titanium is quite good. And in between, there's a gap, right? We can fill that gap with zinc alloys that are biodegradable. The biodegradability, especially, is very important in medical performances because it removes the necessity of a secondary surgery to remove the implant. And also it removes the concept known as stress shielding, which is when implants take over the load, so bone density gets lower because bone doesn't carry any load. Well, this was my presentation. Thank you for listening, and hopefully I'll see you again.